Welcome to the plenary keynote 3 of IEEE Services 2021. I'm Ron Chen. I'm honored to introduce to you the keynote speaker, Professor Amit Sheth of the University of South Carolina. Amit is an educator, researcher, and entrepreneur. He is the founding director of the AI Institute at the University of South Carolina. Current area of his research includes knowledge-infused learning and unexplainable AI, and application to personalized and public health, social good and preventing social harm, future manufacturing, and disaster management. He's a fellow of the IEEE, AAAI, AAAS, and ACM. His awards include IEEE TCSVC Research Innovation Award, University Trustee Award, 10-year award at the International Semantic Web Conference, Ohio State University Franklin College Alumni Award, and Ohio Faculty Commercialization Award. For several years, through 2018, he was listed among the top 100 most cited computer scientists. 3 of the 4 companies he has founded or co-founded involves licensing his university research outcomes, including the first semantic web company in 1990 that pioneered technology similar to what is found today in Google's semantic search and knowledge graph. And the 4th company is at the intersection of emotion and AI. So let's give a warm welcome to Professor Amit Sheth.
Thank you very much, Ron. Thank you again, Ron. As you can see my title, I will talk about knowledge. I will talk about why today's AI system will need explicit knowledge before it will become more smart, before it will become capable of doing a lot more that we humans expect an AI system to do. Next. So we've been hearing diverse views from the AI community. There are a group of people, there was a paper, Unreasonable Effectiveness of Big Data. There are also people who believe that we need a few more breakthroughs, but otherwise deep learning can do almost everything, or will be able to do everything. And there are others who believe that that would not be the case, that deep learning and or statistical AI is not panacea, is not going to solve all the problems we have. It is far incomplete compared to what we need, what we deserve, what we expect. And hence, next please. And basically what we need is that we need these AI systems to be more responsive, more intelligent. And when you think about what we need from AI systems, I happen to be in the camp that deep learning or any statistical AI technique is far from sufficient. And it is necessary, it is helpful, it is playing important role, but there is a lot more that would be needed. And a lot of new innovations is going to come when we start using knowledge to make these AI systems smarter. So Pedro, in his very well-known paper on machine learning, said data alone is not enough. And so along one theme of my talk is that data-centric AI, statistical AI is simply not going to be enough, and that we need to use explicit knowledge in building the future AI systems. The other theme of my talk, a parallel theme and connected theme, is that we need to raise the level of intelligence that the AI systems support. Currently, I'll argue that the AI systems really have very low level of intelligence, and that for AI systems to be able to do, more of the things that we humans want and need, they will need to actually go up in the kind of abstractions of intelligence. And just one of many many examples I can give is that think about 2000 election. We had Imagine you have access to all the data of social media, news article, polls, whatever. Would it have predicted the outcome that Hillary Clinton will lose? Probably not. It would not. And in fact, all the predictions was that Clinton would win. Well, I did have a software we had built called Twitteris, which became the commercial product, and then the company called Cognovi Labs today, where we did accurately predict the outcome of the election. I predicted 2012 election. I predicted Brexit correctly. I predicted some Senate elections, and I predicted 2016 elections. And then in all of that, as I look back, I was able to use very large amount of data. We could process millions and millions of Twitter posts, for example, or any other data sets. But there was intrinsic human involvement. My own understanding of election and how voting systems work, and how in terms of the time, geography, demographics play the role. I remember looking at, for example, uh, urban Pennsylvania versus rural Pennsylvania in making my call as to who will win the Pennsylvania. And there is so much of that kind of domain knowledge about the election that I had to employ to come up with my outcome. This is something that today's AI systems don't have. This is what the AI systems would need. Uh, and generally speaking, the humans do not rely on the data alone. There's a lot more that happens. There is a theory where humans constantly apply their own knowledge and experiences in coming up with whatever understanding they gain of the data. Currently, 11 million bits per second are hitting your sensors, your sensory device, our eyes, our ears, and so on and so forth. And when we understand from what we are listening and hearing and watching, um, we are constantly using our knowledge of the domain, and we are interpreting it. That kind of thing is not there in the AI system today. That's what we needed. Next. So current AI systems have classification, prediction, recommendation, language processing, text translation, and so on and so forth. I'll argue that these are, these represent lower level of machine intelligence. These are limited set of things that you can do. These are important for certain applications, but they, are what you call as relatively simple things that you ask for AI systems. What else we need? Next. So what we have today is what you see on the left. You see, a focus on a very narrow task, and it is illuminated well, and you know exactly what you're seeing. What we need is human-like broad spectrum behavior for looking after humans, for making companions to the human. And in doing so, we will need high level of intelligence that is broad, complex, and multifaceted. There is a theory of multiple intelligence, and it talks about a whole variety of intelligence that you have to, that humans employ when they function in the real world. We will need that, and there is a long way to go. But in that path, knowledge is going to play a very critical role. Next. So here are some of the high-level capabilities or capabilities needed for higher level of intelligence. There's abstraction, contextualization, personalization, analogy, and causality. I'm going to discuss just a little bit of these, some of these samples from these. My team works on all of these, but for the time we have, we'll take a few examples. Next. So we expect a lot more from AI system than what we have today. As I said, deep learning work on narrowly defined text, and they give a false sense of uh, false sense of kind of having accomplished very smart things, but they don't. Also, we need better forms of machine intelligence. I mentioned that. Knowledge is needed. I already said that. Next slide, please. Among the things we need is to mimic human intelligence. We need to be able to reason, analogy, spatiotemporal, causality. We humans are biased. And then you want to serve a biased human? Well, you want to understand what biases that human has, and then decide whether you want to serve that bias or not serve that bias. That's besides the point. The point is that you need to understand that. We need to understand data in complex needs, and then knowledge will play an important role. Next, please. Okay. So I think I already covered much of it. Next, please. So look at the sentence on the right in the green background. Xanadu quit graduate school to join a software company. When a human hears that, the human is going to be able to make a lot of inferences. The human typically understands that Xanadu is a living young human being who was in graduate school because he quit graduate school to join a software company that had a need for a new employee. See, there are a lot of things. There is a lot of undercurrent that we humans are able to, gain. If today's AI system were to be exposed to the text on the right, they are not going to be able to, infer and understand all the things on the left that the humans would be able to do. So while we know that deep learning systems have done amazing job in some of these natural language processing tasks, that what we have is far from what we call natural language understanding. Next, please. There is plenty of literature and plenty of wonderful position insights into the human brain and into the human intelligence and the human decision making. So in behavioral science, behavior economics, Daniel Kahneman talked about system 1 and system 2. In computer science and cognitive science, we talk about perception and cognition. In AI, we talk about statistical AI and symbolic AI. In cognitive science, they talk about top brain, bottom brain. This is similar to system 2 and system 1 at certain level of abstraction. And human activities involve both of these. Our brains are wonderful at processing lots of data in our perceptual system. So this 11 billion bits per second that we gain, that's being processed on a very rapid basis in terms of understanding your surrounding, the objects you are seeing, and so on and so forth. At the same time, we have this slow thinking process, deliberative planning, that requires that is of different kind. What I see happening is that as we go along, we'll understand that knowledge and experiences, explicit modeling of them, and then including them with the AI systems of today, particularly the statistical AI system, will allow us to support both of these better and to connect them better. in our human brain, system 1 and system 2 processes of perception and cognitions happen very well simultaneously, helping each other. Knowledge will become a very important link to connect the two. Without that, that connection won't happen in the future AI systems that support high level of intelligence. Next. A few years ago, I had developed I had a position paper, a vision paper. I titled that "Semantic, Cognitive, and Perceptual Computing: A Paradigm That Shapes Human Experience." There's a paper, there is a keynote talk. But the point that I wanted to really talk about is that you see on the right hand side, at the bottom right, you see there's all kinds of data. So in this case, we are talking about a patient, and we have all these sensors that patients may have, blood pressure and environmental factor that the patient is exposed to, and weight, and so on and so forth. And that is all data. At the end of the day, uh, what a patient is interested in, what a clinician is interested in, is how well controlled is my disease. Let's say in this particular example, we are talking about asthma. And the asthma can be well controlled, not well controlled, very poorly controlled, whatever that is. And that we go through the level of abstractions necessary from that low level data to that high level of understanding on which we can act. If you understand that your disease is not well controlled, then doctor has said to take this extra medication, controller rescue medication for asthma, and you'll do that, right? Now, as one of the things that I portrayed in this architecture was to show, on the right hand side, you'll see various examples. It shows specific explicit knowledge that get used along with statistical techniques to go from that data to actions, decision making, understanding. Next. Next, please. So the knowledge come in variety of form, but two main form is tacit knowledge and the explicit knowledge. And the current AI system, at least the so-called wave 2 AI system, or depending upon statistical AI, is largely depend upon tacit knowledge. They have patterns, and patterns have some meaning, but the meaning cannot be explicitly talked about. So that tacit knowledge, while in a deep learning and in neural network system is playing important role, it is simply not surfaced. And because it is not surfaced, it is not very useful for some of the things. For example, in human communications, we use explicit knowledge, and we refer to the explicit knowledge that you and I know, so that I can effectively communicate to you, with you, right? So we need to again, this talk is going to throw light on this explicit knowledge. Next, please. Next. And one of the interesting thing to note is that the kind of knowledge that we are going to have and they're going to need is going to come in many different forms. One of the best understood form of knowledge is what we call domain-specific knowledge. You can see on the top right. And so, for example, I have a knowledge of a medical domain. I have a knowledge of cars and car scenes. I have a knowledge of smart city. I have knowledge of disaster concepts, and all that knowledge typically is modeled as a knowledge graph or ontology, and this is something we understand well. What we have argued is that we are going to need knowledge of many different kinds: individual knowledge versus group knowledge, we'll need, or collective knowledge, regulation and law. So when I talk about autonomous vehicle, it's not just going to be about driving the car, but it is the car in the context of society and the physical environment. And you'll have to model that. You'll have to model common sense knowledge. You'll have to model social norm-centric knowledge versus individual knowledge. An individual has, let's say, a culture. That individual's culture knowledge will have to be modeled. So this is a challenging job, but we are making progress towards that. Next, please. So one of the way I will explain you in a little bit of depth is that uh, by looking at NLP versus natural language understanding, how you cannot do take the techniques that have worked so well with NLP for natural language understanding, and why knowledge is playing or will play a central role in in natural language understanding. Next, please. So here is a web forum. This is the web forum kind of data that we had used in a project where we made something called what is called as lopremite discovery. So we analyze a whole bunch of web forum data, millions of posts, and we came to a discovery that people who were using opioid were abusing buprenorphine, imidazole, a over-the-counter drug, uh, in 10 to 20 times the prescribed dosage to manage the withdrawal side effect from the use of opioid. But in the process, we have to understand what are the drug users, what are the what are the people who are abusing drug talking about. And in understanding all of them, you come across very challenging text. You come across the text called bup or bup. You can see that underlined blue term bup. You can come across the word subaxone. It is important to definitely understand that they mean the same thing. Bup or bup is a slang or street name. Subaxone or Subutex is a brand name, and the generic name of the drug is buprenorphine, which has certain features, which has certain properties. And there are many other things you need to understand, such as the route of administration, whether you're snorting, whether you're taking injection, all that kind of stuff. You have to understand dosage, sentiment, variety of relationships that are shown on the bottom left, right. When you want to do this granular understanding, this is not what you get from a complex pattern. This is something that has to be unearthed. This is something, and that a human decision maker, in our case, epidemiologists need to be able to understand explicitly what this language says, right? And there are many challenges that you have to face. For example, for every one occurrence of buprenorphine in the corpus, there were 34 occurrences of all the different variations like bup, subutex, subaxone. Now imagine the kind of recall you would have if you did not know that, if you did not have the explicit knowledge representation of the type shown on the top left, right? So we need to really we really need to go to we need to really resort to this kind of representation to be able to understand the language. Without and the argument is that a statistical learning method would not give you what you want. Next. So think about understanding the natural language. When you want to understand that, you are going to employ your understanding of language structure and grammar, syntactic structure and grammar, like what you do in a parse tree. You're going to apply linguistic knowledge, like what is captured in WordNet. You're going to apply common sense knowledge, like what is captured in ConceptNet. You're going to apply broad, general purpose knowledge, factual knowledge, like who is the president of the US right now, like what you may find in Wikipedia or Wikidata and DBpedia. And you're going to use domain-specific knowledge of a variety of domain, medical domain, pharmaceutical domain, autonomous vehicle domain, so on and so forth. All of these are being applied by human brain when we understand a natural language. Imagine what's happening today. I think we are claiming that there is the NLP systems are doing wonderful. In reality, really not. What I would like to share with you is that we have created artificial artificially low-level evaluation strategies and test. What the best known is this GLUE or super GLUE, general language understanding evaluation. Basically, I would argue that there's hardly any language understanding going on there. It is fairly low-level representation, and then you keep a low-level standard for saying, do you understand the language? And then you say you do very well, show 90% result or 92% results or something like that, and say, oh, we are doing fantastic. Fine, but you're doing fantastic with regards to very limited and low-level tasks. We really need to think about high-level tasks. One, what we call knowledge-intensive language understanding, and there is work going on that line. For example, there is a system called Ernie or NoBird, or we have built something called KI-Bird. And then what we are trying to do is to essentially talk about language understanding at high level, and come up with the test to really measure at that high level. Next, please. Here is an example, of what would happen if you do NLP versus NLU in a little chatbot. So the person asking, tell me more about BUP. Well, the chat box says, I don't understand what that is. Then say, okay, I don't understand. So the person says, Subutex. Sorry, he says, I don't get it himself. Then he says, I meant buprenorphine. Now the system understands it because it has a very limited knowledge of the domain. On the right-hand side, the system has the knowledge of the buprenorphine and BUP and Subutex and Suboxone being about the same. And not just that, it also has a lot more granular information about, let's say, what buprenorphine does, or how it is used, or what are the problems in using buprenorphine. And you can see at the very bottom of the conversation that it says, well, this is what happens if you use buprenorphine, right? And that really takes domain knowledge, trying to understand all of the things you see on the bottom right from using a statistical AI technique, deep learning technique, neural network technique. Is something that I don't know how to do that effectively. Next. Here is an example of intelligence that an asthma or lack thereof that an asthma virtual assistant could have. On the left hand side, the user asks, how is the weather today? And the system uses a web service, goes to the weather.com or wherever, and gives you the data. On the right hand side, the system has contextualization and personalization. So the context is asthma. Personalization is what are the factors that lead to the symptoms related to asthma for this patient. So when the patient asks, how is the weather today? It says, well, the ragweed pollen is high. Or low, and then based on that, it gives you the recommendation, right? And because the system knows that personalization is about the system knowing that the patient is symptomatic to ragweed pollen, right? Next, please. So in this building of this kind of conversation, AI-based system that supports knowledge infusion for language understanding. It supports personalization, abstraction, and continuous contextualization. So in a conversation that is long running, what happens is that you go from one area of discussion to another area of discussion. For example, in a chatbot or a virtual agent, you may have conversations surrounding understanding how is patient doing today's symptom. You may and then later on it goes on to kind of understanding the doctor's order and what should be done. And then it may be about planning as to how can you maintain good health. So the context drifts or shift over the period of conversation, and you have to keep up with all of those things. Imagine again trying to, all what I'm arguing is that in doing personalization, having these abstractions you need to understand information and data at different level of representation, and having this context representation and changing context, you really need to have a substrate, like a trellis on which you can train a vine, which is knowledge. Next. So, there are many domains. I listed just a few of them that we work with, where we need more intelligence and as a corollary, use of explicit knowledge. Next. So, here I'm showing you an example of driving. In this particular case, we had for the San Francisco Bay Area data from the road network for the entire year. So billions of data points of cars passing the road, how many cars per road in a given minute on a given road. And then we have all the traffic related tweets filtered out, semantically filtered, also from the area. And then we are trying to connect, is there a tweet that is relevant to this traffic accident? So because of the traffic accident, there is a slowdown of traffic. You only know from the network data, from the sensor data, that traffic is slow at this location. You don't know why it is slow. And here the system connects to potentially relevant tweet that may say, oh, there's an accident on the Golden Highway at the Viking robots in Devlen, and whatever those that text in black is on the top right. So to connect the slow traffic and accident, you are you're making this connection. However, this connection becomes possible only because we use multiple knowledge bases. In this particular application, we use 3 different knowledge graphs or ontologies for smart, for transportation, for smart city, and for other weather and other things. Sorry, for road networks. And that allowed for the connection. Otherwise, how do you build an AI system that is very good multimodal, and there is a stream of data for sensor data and multiple sensor data and textual data like Twitter data, and you need to make a high quality connections, correlations between them? How would you do that, right? So explicit knowledge plays a huge role. Next, please. The next thing is, a very important area of analogy and abstraction. Abstraction is what gives humans the ability to generalize from the situation that he or she has not seen before. And analogy making gives us conceptual understanding needed for abstraction. Often we can, create say, oh, this is similar to that I've seen. It's not the same. And you create analogies in your brain. It so happens that so today's AI systems are pretty brittle, and they really can't generalize from a few examples to understand something. They need millions of data points, and so there are efforts to go in few shot learning and zero shot learning and many things of that nature. I don't think that they are going to be as powerful and effective without explicit knowledge again. Next, please. So, the concept of abstraction is very, very powerful. On the right-hand side, there is a very old a picture that I put down, where there is a specific cow and the concept of cow to livestock to farm asset to asset and then wealth, right? So see how the things have moved from, and our human brain does this fantastically well. You might have some very low-level information or data, and you are transported to talking about some very high level concept or high level abstractions. So and there are some examples here. You have Granny Smith apple. From apple you go all the way to health, right? Or and there's another one, creativity, that I portrayed. This is a very powerful thing that humans do. And you really, if you want to build future smart intelligent systems, we need to figure out how to do this. Again, in my view, the statistical AI systems are very, very poor at this kind of stuff. Next, please. So, and those who do educational pedagogy have argued that analogy is a very powerful way of learning. There is a lot of literature on that from in education, but we've not been able to build a good AI system that does analogy yet. So here is an analogy that are one of my somebody I know, a professor at Tennessee. He for used in his biochemistry class analogy, and he asked his students to build analogy about biochemistry. On the right hand side is a electron chain system, which essentially results into creation of ATP and basically energy transport mechanism. So there is a electron channels that lead to ultimately an activity that transfers energy from one form to another form, and supplies the energy to the cell where it is needed. So the electron transport that you have on the right hand side, somebody draws analogy in terms of pumping the water from the well, where the string, the rope, plays the analogy with the electron transport mechanism. So in the body, and that analogy is very powerful to help you understand what's happening in a complex, analogy. Complex scientific concept that you're trying to convey on the right hand side. Next, please. So these kind of things requires systematicity and the process constraints for kind of describe sequential process. And when you have to talk about variety of concepts that form a sequence of steps in a process, this is very difficult, almost impossible to do if all you have is some patterns, some statistics on the data. You really need some explicit knowledge to be able to do that, and you really need knowledge graph is the mechanism that we use. Next slide. So here I'm showing the analogy that has been built to explain that analogy on the previous slide, between the pumping the water and the thing that happens in the energy conversion. And so there is a villager pulling rope provides energy, electron transfer on transport chain provides energy. Rope is equivalent to electron transport chain. These are specific set of activities that you are trying to portray, and there is the whole process that you're trying to portray. I find it hard to imagine exactly how you can get this achieved using your choice of deep learning algorithm. Next, please. So there are a whole variety of high level knowledge that that we use for planning, for abstractions, representation, for process knowledge, and so on and so forth. And they will ultimately have to be modeled to and supported and used in AI system to get that high level of intelligence. Next, please. So here, you use knowledge to think, compile relevant knowledge for abstraction and reasoning based on task and observational data, and that allows you to think. Then you abstract observations, you abstract observation data by mapping to a compiled knowledge, meaning doing thinking to form human understandable concepts. We call that abstracting. Then you synthesize reasoning over the concept using relevant knowledge compiled during the thinking phase, resulting in action. And then you execute action to enable the decision. You convert the decision into you decide and you act. So these are some of, and these are the things that humans do all time and again. You do every day, every month, many times in a day. Knowledge has central role to play in all of those things. Next, please. Now I'm going to take a few minutes, just about 10 minutes or so, to give you a little bit of a deeper view on how do you we talk about a lot of what's and why. I want to talk a little bit about how you actually incorporate knowledge in the current state of the art AI systems, statistical AI systems, and what does it do. One of the most important thing that one of the most important reason why we need explicit knowledge is to be able to explain. There was a report that just came out from IBM this year, where 91% of the companies said they need and they want the AI system to be explainable. So explainability is going to be hugely important topic. Trust in AI system is recently Steve Jobs said, not Steve, sorry, the CEO of Apple said that just this year that the trust in AI system is pretty low, and we need to increase that. Without trust, technology will not achieve its objectives. So exploratory is really going to be a very important area. It's already an important area of AI. Now what happens is that currently we are doing some decent progress in interpretability of the AI system, but what we argue is that really you need this knowledge, explicit knowledge, to be able to explain what an AI system does. Let me say a little bit more about it. Next slide, please. So there are deep learning models that do parameter visualization methods, and they could highlight, for example, phrases in a text, and in that sense it provides interpretability. But there are phrases that pattern recognition cannot detect very well, and knowledge traceability provides explanations on the model outcome in terms of the concepts that domain experts understand or the user understand. So we are increasingly building AI systems that is used by humans to assist humans or in place of humans. And when we build these systems, we need to be able to explain. But not only that, we need to be able to explain, we need to be able to explain in the terms that is meaningful to the user or the expert. So one of the reasons why some of the deep learning system, let's say image classification system, have performed better than humans, let's say radiologists, and yet clinicians would not use those systems because there is no way for those systems to describe how and why they came up with that particular recommendation or outcome. And without being able to explain really basis on not just what data, but what medical guideline are you making this prediction or a recommendation, right? So think about it. A clinician is not going to even react to what only data. He is going to use medical guideline. He is required to use medical guideline. He can lose his license if he is not he can lose his license if he does not use medical guideline and explain why he has made that choice or decision, what on based on what. That medical guideline is the knowledge, is the domain knowledge, and that needs to be represented explicitly in case you want to generate an explanation from the data, right? Next, please. And the clinicians will understand what explanation only if you phrase it in the in the context of that clinical guideline. If you just immediately come up with saying, I have this lot of abundance of data, and this data is meaningful, and attention mechanism has shown that this data is relevant to this outcome, so what? It doesn't say anything to the clinician. Why that phrase, that data, that reading from the patient in the context of a given medical knowledge, clinical guideline, takes you to makes you believe that indeed patient is suffering from this or that. This is diagnosis or treatment. This treatment has to be done, right? So there are many ways to. So one of the things that we do is to incorporate or infuse knowledge in AI tech. Current crop of AI techniques, largely we're talking about deep neural networks. And so we wrote a paper called Shades of Knowledge Infused Learning, and we provided the classification of three broad classes just for pedagogy simplicity. On the left, you see shallow infusion. What happens is that you take the knowledge and dumb it down into the form that in which data is being processed, typically as a vector. So basically, you do embedding. So knowledge graph embedding is a very well-known technique, and people have used it very often. And that is the way of infusing the knowledge. Unfortunately, that technique, while shows some better results compared to not using the knowledge, doesn't achieve a lot of things that is necessary. And in particular, it loses out on the richness of knowledge, because ultimately, when you represent knowledge, you use a knowledge representation, knowledge representation, whether it is a triple or a graph or a label graph or a probabilistic graph. There are many forms in which you represent knowledge. That richness, expressiveness of knowledge representation has a huge value. And essentially, what has happened is that the expressiveness of deep learning, data-centric technique is very low. So when you dumb down the knowledge graph, the knowledge in the knowledge graph to this text, then you lose out a lot. So shallow infusion is that. Now, in the semi-deep infusion, what happens is typically at the output layer, you use the knowledge to modulate the parameter and change the functions, attention, for example, based on the knowledge. So different weights allow you to, focus your attention to different parts, and you are using the knowledge to guide your attention, and that leads to potentially better outcome, and that those are semi-deep infusion techniques. Next, please. A couple of examples, or let's just one or two examples. So go back, please. Yeah. So here you see a text there, and this is posed as a well-known classification technique. You want to predict what is the mental health condition. This is from a Reddit, mental health related Reddit, and the system comes up with is this mental health related? 71% for that. The next would be what mental health condition. It says depression. Actually, the answer is wrong. The correct answer is OCD, obsessive compulsive disorder. Why? Next slide, please. By the way, the highlighted terms are the ones that are due to the attention metrics. So here is a technique where you use. Can you go forward, please? Yeah. So here is a method that shows use of a knowledge infusion, and essentially what it shows is that on the left hand side you see this DSM-5 knowledge. DSM-5 is the documentation or medical text that are used, kind of Bible for all the mental health professionals. This is what all the mental health professionals are trained on. So we extracted knowledge from DSM-5 and created a this correlation matrix involving both the data from the post and the DSM-5. So you see that matrix there, and use that to change the functions there, weights, and that leads to a higher confidence in mental health. That it is mental health related. Now you're getting 0.82 instead of 7.1, and this one is resulting in predicting the correct health condition, OCD, right? So it shows that the use of knowledge, and what are the things that contribute that. One of the interesting things that happened is that LGBTQ or bisexuality came up as items that received the attention, which was not the case in the previous example, without the knowledge graph. And that shows that use of the domain knowledge can lead to and like would usually lead to better outcome, right? That the bisexuality and LGBTQ are the knowledge relevant to OCD that were obtained from DSM-5 that were applied here to get what you want. So it's a very powerful support for the value and need for knowledge here. Next, please. But now what you want to do is you want to be able to create explanation that is understandable for the humans. Why is this OCD? Why is it not something else? And what happens here is that here we have replaced the terms by the appropriate types of classes. So there is a health related behavior, and there is a level of mood, and there is drinking involved, and and then there is a mention of OCD disorder, personality disorder, and then disturbance thing, all this kind of stuff. So it says, it gives you insight into the kind of factors that got involved. Now remember, these factors are not in the text, so a data centric mechanism is not going to get that, right? Go next slide please. Yeah, so see what is happening here is that you are doing here what is called as lifting of concept, so you have text here. Text as concept called bisexuality, or worthless, or we get drunk, right? Then what happens is that we are lifting that to the concept framework. We are mapping that to the concepts in the knowledge graph, and that will allow you to have deeper and better and understanding of what that text is about and what is its relevance to what you are trying to do, such as understanding OCD. So OCD is a disorder in which people have obsessive, intrusive thoughts, ideas, or sensations, and make them feel driven to something repeatedly. So obsessive, intrusive thoughts, these are the things. And what this shows you is that we found the support for that aspects of the definition. So I'm able to say that here is the definition of OCD, and it talks about obsessive, intrusive thoughts. And now look, understanding natural language, understanding of this text with that knowledge, domain knowledge, allowed me to tell you that indeed those concepts are present in this thing, and hence I have classified this to be OCD. And this is how you got, so this is the explanation, and it's an explanation. The definition is what a clinician cares for. So this explanation is in that term. Next, please. Next, please. Yeah. So here it kind of shows you, in that same study that I talked about, that as you infuse different, kind of knowledge or other things, what the improvements there are. So you can see on the left-hand side, the state-of-the-art research result in 2018 that used lexical and statistical features, but it had a very high false alarm rate, 30%. Then somebody used TF-IDF features, so just some more features really, but these are lexical and syntactic features. Slight improvement, 3% improvement. But then you use contextual features, significant improvement, to 13% now, error rate from 30%. Then we used contextual features weighted by DSM-5 knowledge hierarchy, 13% got down to 4%. Additionally, we used additional knowledge of drug abuse. DAO stands for drug abuse ontology. And then finally, we used additional knowledge of slang terms and all the power of knowledge that we could potentially muster, and it took it down to 2.5% error rate. So you can show that the knowledge infusion, use of knowledge along with the data has substantial improvement. And I think this gives you the potential way to say why humans are so good at understanding a language or understanding any kind of sensory input, because we don't have that much of a that big an error rate as some of the statistical methods do. Potentially quite likely because humans apply the knowledge, right? Of course, the right human with the right knowledge, right? So domain expertise is necessary, and you are applying that. So I think there's a powerful support for understanding why knowledge makes substantial improvement over statistical technique, and why knowledge is critical in coming up with the explanation in the form that is useful to the end user, or the domain expert, like clinicians, or like somebody building autonomous vehicle software that needs to perform very accurately. Next, please. So we are continuing to play around with different architectures and different and more sophisticated way of infusing the knowledge. So there is this thing called deep infusion of the knowledge, and what happens is that we kind of think of the knowledge in stratified terms. So earlier, you remember I showed you a whole sort of a whole different kinds of knowledge, starting with syntactic, to lexical, to common sense, to general purpose, to domain. And this is not a fixed level. There can be more depending upon the intellectual activity involved. And I showed you that you could incorporate the knowledge, the lexical knowledge. You could incorporate the common sense knowledge. We built a system called KIBERT, where it infused lexical knowledge from WordNet and common sense knowledge from ConceptNet, and showed that it improves upon the attention without the knowledge. And now we would like to add to it the domain specific knowledge, and show how much further improvement we can get. So the point here is that just like deep learning system is a layered learning system. If you're talking about images, you earlier start with pixels and very low level features of image, and go down to a little bit modest level of abstractions like texture and color, to understanding of objects, and something very high level, that is what you're looking for from a model. Well, with respect to different layers in your architecture, you could you need to understand what those layers do, and then you need to infuse the knowledge of the right kind at that layer, and that then you lead to deeper understanding. What we are trying to also do is to kind of take some inspiration. The neuroscience has not progressed enough to fully understand exactly how the brain works. I think we are far from it, as neuroscience themselves will tell. There's a big kind of a panel that Montreal AI guys put together, and there was a panel on neuroscience and AI. And I think majority neuroscience admit that there's a lot more to go. And I'm not so much interested in understanding individual neurons, although we have now recently learned, just last week there was a paper, that each of the neurons is far more complicated than what it has been talked about in the past, and that's just in neuroscience. Correspondingly, what I would like to say is that the neural network architecture that we have today are toys, are very simplistic. Are the neurons that we model is in the perceptron is incredibly simplistic. If you want to get the compared to human brain, and hence the plan to go to the human level of intelligence. So there are many things that we'll have to think about. We may think about improving the complexity of uh, uh, neurons and perceptual model by infusing the knowledge and retain knowledge in that, and that will be the way of doing about going about thing. And we need to talk about the loops that happen in the understanding, where you go to high level of abstraction, abductive deductive cycle that cognitive scientists talk about. And we need to talk about the thing that in our brain, from the perceptual system to cognitive system, we go to different levels of abstraction, and we employ different kinds of knowledge. For example, we may, at a lower level thing, we may be applying our spatial knowledge as to where we are in the space. At a high level knowledge, and the level is kind of, depends on you to define the level, what you mean by level. But high level of knowledge, you're talking about a very specific knowledge about the domain for which you're going to make a decision, like say clinician, or autonomous vehicle, and so on and so forth. So there is, what going on in my group, and I'm sure others would be interested in working on these things too, called, deeper infusion of knowledge. But the most important point to take away is that I see the future systems who are going to strongly integrate the tacit knowledge with explicit knowledge, the statistical AI with symbolic AI, and the in creation of this neo symbolic computing system. And basically, I feel confident that knowledge, explicit knowledge, and its exploitation will be a hallmark feature of building the neuro symbolic computing systems of tomorrow. Next. So to conclude, then, DARPA talked about three waves of AI. And they talked about the first wave of AI, and some people may call that symbolic AI, 1980s and 90s. I remember, having a DARPA project in 1988-89 for integrating AI system with database systems. And in those days, in AI systems, we used to talk about interpretive logic was the main, basis for knowledge representation for building AI system. We used the expert system, which is rule based, or there's a prologue that interpreted style of learning, to a system that was developed called LDL for compiled style of learning. And as those systems process, do the reasoning, they need facts or knowledge from database. So how do you supply the knowledge from the database efficiently to those systems, interpretive to compile? That's the kind of work that we did in those days. But those were the days of handcrafted knowledge. I myself remember building an expert system for chrome plating of military aircraft landing gear. So hand coding rules by reading the text with a book on that, and then having the expert verify the rules that we had encoded, and then running the expert system. Then came the second wave, the also called as statistical learning, and really they have done I guess wonderfully well. The AI is everywhere, and it is thanks to machine learning of the first decade of this century, and deep learning, starting 2012. And it has done some things very well. But remember what I said earlier in my talk, they do like narrow activity, and in that narrow activity, well-defined, limited activity, they have done fantastic. They can beat humans in doing those activities. But the next one, which also some people may call it neurosymbolic computing explanation, then you will just this needs contextual adaptation. The ARPA used the word contextual adaptation. Now I kind of describe in my own way what I mean by contextual adaptation, and I also emphasize the explanation very well. The system understands why it is making that decision, and I argued that explicit knowledge is going to play indispensable role in building these explainable AI systems, which everybody seems to want. Now that everybody seems to see that AI is very important for them, there is a CEO of Bain Capital, who said every company is an AI company, right? So that's tremendous interest, and of course, huge hype, and that even knowledge graph term is considered to be a hype now at the top of the hype curve in DARPA. But the next thing, and that it may be or may not be, but the next thing is that to deliver the uh, promise of AI, we need to combine both the knowledge and the statistical learning techniques to build these more intelligent systems that represent high level of human intelligence. When a chatbot talks to human, it needs to have deeper understanding of human emotions. It needs to have empathy, and many of these things will have to be built future in the systems. And because humans use explicit knowledge to communicate with each other in a very prominent way, the same way when the AI system has to communicate or assist human, the AI system will have to be built on the top of explicit knowledge. And so one of the interesting thing that my group does is to and the AI Institute is that we learn from broad variety of disciplines: neuroscience, cognitive science, behavioral science, behavioral economics. In fact, just this year, we hired two new faculty at the intersection of neuroscience and AI. So they are part of the AI Institute, but we closely work with Institute of Mind and Brain, and psychologists and cognitive scientists and neuroscientists in our university, at multiple in multiple centers and institutes. So we also, I work with a colleague, a long time partner in my research. Her name is Valerie Shellin. She's a psychologist, cognitive scientist, and of course some wonderful ideas have come from behavioral economics. So these are just some of the things that we take inspiration from. So with that, the next slide is just a thank you note. If you may briefly show, and then we can. I'll post the presentation online, which will have some backup slide with a lot of details. Of course, thanks to a lot of funding. Currently, we have about 20 projects funded at the intersection of AI and whole variety of disciplines: smart manufacturing, neuroscience, public health, medicine, and nursing, and so on and so forth, and social sciences. And just a couple of them that are relevant are listed here. And some of my students who helped me with the specifically putting together these slides. So thanks to them. All right, so I am going to pass on to Rong now, I believe, and thank you for Rong. Thank you for inviting me. I hope it's been useful. I've just taken over an hour, and happy to take any calls or talks.
Yeah. Yeah, Amir, thank you very much for this insightful speech. So now we are starting the Q&A session. So audience, please enter your questions in the Q&A window. And in the meantime, Amir, I have one question for you. Are knowledge graphs ready to keep pace with deep learning?
Yeah, so the deep learning of machine learning, if you may recall, got a lot of people interested, and deep learning also got a lot of people interested, and the number of people working on deep learning far outstrips the number of people working on knowledge graphs and that semantic technique. So even though ontology and knowledge graphs are not new concepts, very old concept, the rate at which they developed has been somewhat slower, and biggest problem has been the tooling. So there have been Veka toolkit for machine learning, and there are all these deep learning toolkits available for us, PyTorch and so many other things. Now that has made deployment of AI techniques much easier. If you compare with that, the knowledge graph techniques are the tools necessary to build knowledge graph has been far more limited. One of the projects that I have actually is about building a knowledge graph. It so happened that when I did my second company, this was the first company that is web-based semantic search using knowledge graph, and we have patent filed in 2000, award in 2001. So patent was filed before the well-known paper on semantic web, which had knowledge graph and which used knowledge graph for search and for other things like showing info box that Google shows. But problem was that knowledge graph, if they're manually built, then they can't keep up with the pace of innovation in the deep learning, where you're massing enough data and all this algorithm and high-end computing available. So that is changing, but has not changed. However, there is one advantage that the knowledge graph people have, and is that humans have collaborated, what you call as collective intelligence, to create knowledge that can be easily tapped and converted into useful knowledge graphs that can be used in the neurosymbolic company system. So people have done WordNet by hand, ConceptNet by hand, Wikipedia by hand, Wikidata is updated by hand, UMLS is generated by hand. All of this is done by hand by a lot of people already. They are there to be exploited. So on one hand, for many AI systems, many sources of knowledge are already available to create and modify the knowledge graph necessary for those AI systems. Yet some more work is needed, where we need to have tools to build the dynamic knowledge graph dynamically. This knowledge is not static, so they need to keep on changing, and the tools need to be able to support that. So that work is still following, and it will take, I think, another 2, 3, 4 years before we have something even more solid. But so I would say largely yes, but not exactly, not fully.
Okay. Yes, thank you. Now we have questions in the Q&A chat. I don't know if you can see that. The first one is, where would you classify the capability of IBM Watson? Is it knowledge intensive?
Well, I mean, the Watson did use DVpedia, as we all know, and so I give credit to Watson for realizing the importance of exploiting knowledge. I mean, because the Jeopardy, for example, is very fact based in a way, and the facts are there, represented in some form that can be transformed into the form that your Watson system can use. Clearly, their use, although eventually I understood their use was limited, but their use was refreshing, and that was very important. And I have personally 4, 5, 6 PhD students, former PhD students, who have worked for IBM in Watson and Watson Health. And so I have some, of course, some continuous kind of understanding while Watson was very hot about what's happening there. And yes, I think that Watson, many efforts in Watson's and Watson Health did exploit and try to exploit knowledge in and knowledge graphs. However, not all. So I think that the Watson effort was really done before we have now better understanding of how to, this whole thing about knowledge infused learning that I talked about today is more recent than Watson effort. So during the time of Watson, the best that was done was very loose coupling of a variety of other AI techniques for recommendation. Basically, ultimately, it was primarily a recommendation system. The use of knowledge was very loosely coupled kind of thing, and so the power that you gain from knowledge was also very limited. In that sense, yes and no again answer is a nuanced answer. It is I would say that some of the creators of Watson clearly knew the value of knowledge, but a lot of systems that I saw them being built for, they had Watson Health for pharmacogenomics. No, so pharmacovigilance, for example, or they had Watson Health for variety of market verticals. Some had more knowledge, others had very little knowledge. And one of the reasons for that is something I would like to explain. This is very important. Largely, today, if you look at all the National Science Foundation funded efforts in AI, workforce development is very big thing. One of the interesting thing I have observed for a long time is that the amount of education that we give to our students about knowledge and use of knowledge in building a system is minuscule, maybe less than 10% of amount of the knowledge and training we give to our students in teaching them machine learning and deep learning. So if you want, so my proposition is both are equally important. One is not more important than the other, and that unfortunately, though, in workforce development, we have done ridiculously small amount of effort in training the students for what it would make to build this more intelligent AI system. It may be justifiable because people were picking lower hanging fruits, and they really, so okay, they were happy with some recommendation and classification and so on and so forth. And for that, the AI system did, the statistical system did very well. So they were all went for that, and they got good jobs if you know machine learning, deep learning, and choose the right algorithm.
Yeah, thank you. Here's a very good related question. What should be the objectives of AI systems? Should it be to emulate human capabilities or augment human capabilities?
Oh, this is a softball question. This is a wonderful question for me. Thanks for asking me that. So in 2008, I had given a keynote, and I had also a paper called "Computing for Human Experience." And in that, I had portrayed the different visions of AI. In that picture, on the left-hand side, the vision of AI was the Marvin Minsky vision of AI, where AI is replacing human. And then there were other visions of, by Ted, I'm forgetting all the names on my mind, by Mark Weisner, competing for 21st century, related to ambient intelligence, where sensors are around. Another vision for human-computer symbiosis. So there have been community science, not hardcore AI, but community science influenced AI visions. And on the right-hand side was what I called computing for human experience. So my personal vision was extrapolation of what Mike Weisner and others had said, in that I felt that AI system is there to not at all replace human. And on the low level task, they can replace human. That's not a big deal about it. If there's a repetitive task, they replace human, that's fine. But I am really interested in that part of the AI, where the AI system is there to make human life better. When I say improving the experience of human, I mean that I want human to be having more entertainment. I want human to have better health. And the health is a very good example. My interest is, you're not impressing, you're not going to use AI to replace human for human health. You are going to use AI to assist human to keep better health. So I came up with an initiative called Augmented Personalized Health, where you use all kinds of sensory data, all the biosensors, all the patient-generated health data to kind of monitor, appraise, and manage a disease. And we have use that for asthma, we are doing it for diabetes, we are doing it for hypertension, we are doing it for training the parents of autism. So we are doing all these things in the context of virtual health assistants and other things which use a lot of sensory data and a lot of innovative interactions with people. But the objective is to improving human health. So it is to improve the human life and human experience. That is what I'm interested in. That is a form of AI I'm interested in.
Yeah, thank you very much. Okay, now thank you again for delivering this insight for Keynote. So we now conclude this session. Thank you very much.
Bye.